Okay, so what we're going to do today is actually quite a lot. We'll look at correlation, regression, and talk a little bit about two-way Anova as well. Okay, then the last part, we're going through your test papers here. Okay, so today what we'll be doing is on regression or correlation and regression. You are using this new data set called Algae. But because we want to do in Excel and R, so make a copy of this Algae data set. Just in case you so you call this as Excel. So you use the Excel for Excel. Okay, otherwise when you go to R, you're going to have a problem. So we keep the original data set as is. Okay, so you open the Excel data set first. Who is this guy? Okay. All right. So in this data set, what you can see is we are looking at algae bloom. Okay, column M is the amount of algae. It can be in growth rate and percentage. We really do not know. Okay, we have to go to actual paper and find out. So column A. Yes, Keith. Column A is the numbers. Okay, so we don't ignore that. Then B, C, and D are categorical variables. Okay, the rest are actually chemical concentrations. So indirectly, we are trying to figure out how to use chemical concentration to look at algae growth. Make sense? So what we are trying to do is really this thing. We are looking at algae. For example, is algae growth affected by just, for example, potassium? So when you do your regression, you're actually looking at your phosphate. So phosphate, not potassium, phosphate, and your gradient. Right? So this is your linear regression first. All right, this is the same way as what you see. It's equivalent to what you know in your secondary school, your y equals mx plus c. Okay. But statistically, we don't use m and c. We will write it as algae equals to the y-intercept. We always denote it as beta 0. So it's coefficient 0. Then the rest, m is beta 1. So when you see me talking about beta 1 and beta 0, that's what I mean. Okay, make sense? So we can actually look at different models. We can actually say that is algae growth affected by phosphate? Then what else we have? Yeah, affected by phosphate, and is it affected by chloride, and so on? Okay, for example, here is talking about nitrate. Okay, so if the equation is just your standard y equals mx plus c, we call this as a simple linear regression. Okay. If it's more complex, like for example this situation, right? It is still a linear regression, but it is called a multiple linear regression. Okay. So you ask me, why is having multiple variables still called linear regression? Right? Likely that this equation is not going to be a straight line, right? So why is it still called a linear regression? The term linear here refers to the index, or what we call as the power of the coefficient. All the coefficients have power of 1. That's why it's still called a linear regression. All right, make sense? So an example of non-linear regression will look something like this. Okay, you seldom use this. For example, we can have algae equals to beta 1, but it is to the power of n, maybe to the power of 2 to the power of 3, and so on, of phosphate plus beta 0 to the power of m. That is non-linear regression. It's very, you seldom use it, to be exact. We don't bother about it so much. So far, okay? So that's the concept. All right. So the very first thing we want to do is to look at correlation. Are two things correlated or not? For example, is the organic phosphate correlated with the phosphate? Make sense? Okay. So in your lecture, how many correlation do you learn? How many correlations do you learn? Yes, what? How many? How many correlations you learn in your lecture? Or you heard of? Okay. So for correlation, okay, there's actually, at the moment, you only learn your Pearson's correlation. Have you heard of this thing called Spearman correlation first? Is it in lecture? Right? When do you use Spearman's correlation? When? Huh? Non-parametric. Pearson's correlation means that the data must be normally distributed. Okay. If the data is not normally distributed, then you use Spearman's correlation. So far, okay, right? In Excel, you only have Pearson's correlation. Okay, in Excel, there's only Pearson's correlation. In R, you can do everything. Okay. So how do we do Pearson's correlation for, let's say, these two variables? Or, okay, let's reverse it. Anybody know the equation for Pearson's correlation? Oops. What is the equation for Pearson's correlation? To find out, let's look at it. Where is my Google? Mr. Google. Okay. Pearson's correlation. Okay. So this is the formula. You remember? So it's actually not very difficult. It's just a summation of x itself minus the mean of x multiplied by y minus the mean of y. Okay. Then the denominator. The denominator is the summation of x minus square and okay, but you realize that x, a number times a number is square, but here the denominator is the power of 4, so you have to square root it. So that's the equation. Okay. Okay, so essentially that's what it means. So how do you do it in Excel? Let's say I want to find out the organic phosphate, the PO4 and PO4. The easiest way is just use a formula. The formula is called correlate, C-O-R-R-E-L. You take equals CORREL, correl. Then it asks you array 1 and array 2. It doesn't matter which one is X and Y. Because from the equation, it doesn't matter which one is X and Y. Okay. So you take X to be organic phosphate, Y to be phosphate. Okay. And that's all. And you get a correlation of 0.914. So far, okay? This should be quite easy. So you can, and the easiest way, the nice way is you can go to the equation and you can actually drag the block as well. So now I'm doing the correlation between ammonium and phosphate. Okay, it's a much lower correlation. Okay, because as you expect, phosphate and organic phosphate should be correlated to some extent. So far, okay? You can do one correlation already. All right. So then let me ask you another question. If you want to do a correlation with all these, okay, let's say you want to do a correlation with all the numerical data points. That means is your, let's say your nitrate correlate with ammonium, is nitrate correlated with phosphate, is nitrate correlated with organic phosphate, and so on. So you want to do everything. Okay, you can use the same method as what we did just now, but it's going to be very tedious, right? You're going to do pairwise for everything. Okay. So now we can use your data analysis tab. Go to data analysis. Just go. And you look for this thing called correlation. Okay, look for correlation. And ask you for the input range. So you highlight everything. And the data is grouped by columns with labels in the first row. That's what you always expect. Okay, and for our life, to make it easier, we want to put it in a new worksheet for your correlation. So then the new worksheet name will be for correlation. Okay. All right. So then you click OK. Now, it will give you an error because it contains non-input range. So what does this error really mean? What do you think this error means? You have seen this error before. What do you think this error means? When you see this error, the easiest way is you cannot highlight the entire column. Okay. So you go to input range. You have to select only the data that you want and see what happens first. It may give you error still. Okay. It will still give you error. So what do you think has happened? Okay. If you look at it carefully, you realize that some of the data points have this thing called NA, which means they never record the data. It's not applicable. So you actually have to remove those rows by itself. Makes sense, right? So how do you remove those rows? The easiest way is to sort the data. Sort by, let's say, one at a time, smallest to largest. Then you have kind of remove all those as NA. Okay, so like this pile is gone first. So you delete. Okay, then you sort another one. Oops. Okay. After that, you sort again. Okay, you go from largest to smallest this time. Okay, there's still a few more. Like for example, this here. Okay, so you delete them. Or you can also scroll down and kind of scan through where are all the NA. Okay. So it's actually quite tedious. So this is why when you collect your data, you have to collect your data as carefully as possible. Okay, you kind of go through one at a time, clean up your data in this process. Okay. Then, or you can go and find, is there any more NA in the columns? Oops. So there's one more here. Okay. And after you're done, you're only left with 185 rows. So you do it one slowly. Okay, it's not easy, huh? Yeah, until you can't find it. Okay, because Excel is quite fast with it. Right. Just go to Control F and find where are all the NA, and then you can delete the whole row. Sometimes you do that. Okay. All done? No. Okay. You just do a Control F and find them. It's much easier. Otherwise, you will not be able to identify them. Delete the rows, you end up with only 185 rows. So for those, some of you already done the correlation matrix, that's the correct way to do it. Okay. So once you're okay with it, then you can do your correlation. So you highlight the data points. Okay, and we want to put a new worksheet called correlation. So you click OK. Now it generates all the correlations for you. Okay, so you can see which chemical correlates with which chemical in terms of concentration and so on. All right. So that's an easy way to do correlation. Okay. And you only do Pearson's correlation. So how do we get Excel to do Spearman correlation? There's actually a way. So for example, let me just show you. You can do step by step. Let's say I want to correlate your nitrate and phosphate. So I collect these two rows. I go to my correlation worksheet. I throw the two rows in. Okay, I don't bother about correlation matrix first. So far, okay? All done that already. Now, then what I'm going to do is a trick known as this. I have to rank it. So Spearman's correlation is actually a rank correlation. So I have to do a rank of NO3 and a rank of PO4. So you have these two columns first. You just type in the two labels. Okay, all done. So now what you do is you highlight all the 4 columns. Okay, and you sort. You do a sort with my data has headers. So you sort first by nitrate, NO3. You can sort from smallest to largest. Okay, so let's say you sort from smallest to largest, by convention. So we just sort it. So the data points will be from smallest to largest, correct? Now what you do is this, at the rank, just label them yourself. So this is rank number 1, this is rank number 2, as though you're putting things in order. Okay, so after you put 1 and 2, you can just double click it. It will go all the way down until rank number 184. Okay. After 1 and 2, you can just continue dragging, drag it down. Also can work. Okay, so far okay? Okay. Then since I've ranked the nitrate, I have to also rank the phosphate from smallest to largest. But if I rank the phosphate, do you think the rank of the nitrate will still remain the same? No, right? That's correct. It's not supposed to remain the same. So I highlight all 4 columns again. This time I rank the phosphate from smallest to largest. And click OK. Do the same for rank for phosphate. So 1, 2, and so on. Okay. Now let's look at the equation for Spearman correlation. Okay. Spearman correlation formula is this. What does D means? D means the difference in rank, the difference between rank 1 and rank 2. So D itself is actually here. So D itself, you can take rank of nitrate minus rank of phosphate. That is the D. Okay. Rank of nitrate minus rank of phosphate. That's your difference in rank. The slide. This? Or what you want me to repeat? So here, I'm just taking the difference in the ranks. So you take one rank minus the other rank. Okay. Then you can slowly plug everything into this equation. But I find it very tedious. I never like this equation myself. So I'm just going to tell you a simpler way of doing things. Okay. It's actually not the correct way, but it seems to be close enough. Okay. So let's say I have my Pearson's correlation. Pearson's correlation is nitrate. Oops. Pearson's correlation is my nitrate against phosphate. Right? It's my Pearson's correlation. I want to find Spearman's correlation. Now look at it carefully. Pearson's correlation, I'm taking the original data values. Make sense? That's what I actually did in the first place. Spearman correlation, instead of using the whole formula, which is a bit tedious to type it in, I can somewhat do the Pearson's correlation of the ranks instead. This will be quite similar to the actual Spearman's correlation. Okay. The difference is almost a third or fourth decimal point. Yeah. Then we do again now. We rank again now. We rank again. So you rank. No. So you rank. So now you're nitrate already, right? Okay. Then after that, take this. You sort by phosphate. The data is messed up already. You can retake the data. We're going to recopy the two data columns. Yes, my turn here. Okay. So, let's see you messed up because you doesn't know where to go. Messed up again. So now you start it. 1, 2. Here. Okay, now. Okay. There. Stop. Install. Nitrate. Okay. There you go. Are you all right? Yeah. Okay, so the next part, right? Let's go back to your data set and copy from column E to column M. Okay, and put it into another data sheet, column E to column M. So far, okay? Now, you don't have time to go through everything. You can do the scatter plot method to get your correlation, to get a regression. But now we are just simply going to do the next step. So step number 3, part 3 in your worksheet, you actually can do it yourself. It's actually not too difficult. Let's say I want to find out this. Okay. The algae, is it correlated with phosphate? This is the equation that I want to fit in. And so called by fitting the equation, what I'm trying to figure out is what is beta 1 and what is beta 0. These are two coefficients I need to find. Right? Then I also want to find the correlation as well. These are 3 items I want to find. Okay. So how do I do that? I go to my data analysis tab and look for regression. I look for regression. Okay. And now there are 2 things I need to put. Input column Y range and input column X range. So what is my Y, what is my X based on this equation? Which one is my Y, which one is my X? Which is Y, which is X? Huh? X is what? B1? No, B1 is a coefficient for X. What is X? This is X. Algae is Y. Alright, okay. So that is why I put in. Algae, I put in for Y. Okay. Then phosphate, I put in for X. Don't highlight the wrong column, huh? Okay, and it contains the data labels. So I click the labels. Okay. What I want is the output range. Let me put output range in K, K1. All right. So once you are happy with it, click OK. I'm highlighting, Y is highlighting the entire column of algae, but I kind of select it. I don't highlight the whole column. So all right. Those at home, are you surviving? Let's see. Anyone alive there?
Yes.
Okay, good. Which one? How do I select a whole column? Let's say for Y, right? I can just drag it down to the end of it. That's it. Yeah, I can. Or I use another method. Let's say for my X, right? I go to the first cell, Control Shift down, you will select the whole column. So for Mac, you have to learn your own keystrokes. Mac is probably Control with the Command Shift something. Okay. Yeah. I don't know. Mac, you have to do it for yourself. I don't know what's the keystroke that you use. I haven't used Mac to do Excel for 10 years already. So once you're ready, then you click OK. Okay, some of you have done that. And let's look at this table carefully. So this is your regression table. You realize that there are three parts to the table. You have the regression statistics, which is what is the R value, what is the adjusted R value, and what is the R square. R square is just R times R. Okay. So this is the correlation. Then the second part, you actually have an Anova table. What do you think this Anova table is doing for you? Why does it produce an Anova for you? What is the purpose of this Anova table here? Anyone want to suggest something? Give me a guess. What is it testing, literally? This Anova table is actually to test the hypothesis. It's actually to test the null hypothesis that R correlation equals to 0. That means there's no correlation. The alternate hypothesis is correlation is not equal to 0. Means that there is a correlation. Far so good? Confusing enough? Okay. Again, I'll see how much I can accomplish today because it's a lot of things for you to remember. So where am I now? I've done correlation. Now we are in regression already. Okay. Then after that, look at this third table. Okay. If I were to just make it easier for you to read, let me format the cells. Okay. So what is in this third table? What do you think this third table is doing? This third table, the most important one is this thing called coefficients. Okay. Because just now what we are trying to figure out is actually this equation, right? We are trying to figure out algae, or rather capital algae, equals to my B1 times O4 plus B0. Correct? So this is actually my y equals mx plus c. What this coefficient says is what is B1 and what is B0. So indirectly, it's saying that the linear regression, the equation for the line is actually, but you use the coefficient here. So it is minus 0.0232 plus the coefficient for the intercept, which is 25.889884497. So this is the regression line. So far, okay? So are you happy with up to here now? There are still more things, right? What on earth is this t-stat and p-value? Okay. The intercept t-statistic is 12.7. It's actually testing the null hypothesis that intercept equals to 0. That means it's testing the null hypothesis that B0 equals to 0. And the other one is testing the null hypothesis that B1 or beta 1 equals to 0. since you can test the null hypothesis, outer hypothesis, you also realize that from your t statistic, you can reverse calculate into confidence interval, right? Make sense? You've done it in your test. Some of you did it right, some of you did it wrong. So what I'm trying to say is these coefficients, let's say the coefficient for y-intercept is actually 25.88. 25.88. That is the mean, that's the middle value. But this coefficient for y-intercept has a 95% confidence interval, and this is the upper and lower 95% confidence interval from 21.89 to 29.87. This is why you can use confidence interval for hypothesis testing. It's not exactly wrong, just that it's more convoluted. Okay. So far, okay? All right. Now, what happens if I want to see, do you think this regression is actually good? So my R value is 0.45. Do you think it's giving me a good answer? No, right? So can I say that instead of this, can I say that my algae is actually related to my phosphate and a lot of other stuff, a lot of other chemicals? Possible, right? So we are going to do that. Okay. Let's hide this thing first. Okay, you want to hide or you want to delete, up to you. I just hide it. So what I'm trying to say is my algae, can I predict my algae concentration by using all the media composition that I know? Okay. So what I'm going to do is go to my data analysis tab again. My algae input range remains the same. But my X input range, I go from A all the way to H and select everything. My output range, I don't override. I put it as my U1. So make sure that you got all the numbers there first. Okay. Then if you are confident enough, then click OK and see what's the result. All right. Now you get a R value of 0.55. It's actually not good, but it's actually not too bad either. It's better than 0.2 something that we have just now. Okay. So in terms of statistics, for this module, we say that we want to get your R as high as possible, right? 0.9 and above, or less than 0.9 and less than minus 0.9 and below. Okay. That is not exactly practical in biological data. In biological data, you almost never get correlation that is so high, unless it's lab experiment. Okay. Seriously, you are never going to get good correlation. In fact, for most biological work, let's say you're doing genomics and so on, a correlation of 0.4 is actually very high already. Okay. Then the third table is pretty complicated because it gives you all the coefficients now. Right, that is all the coefficients for you to use. That means algae equals to minus 0.0917 of chloride plus minus 0.04574 of phosphate and so on. So that is the whole regression. So far, okay? And then you do all the t-tests for every single one. All right. So can survive, right? We are only like 1/3 of the whole thing, you know. Okay. There's a lot more. There's a lot more. Okay. So let us go and repeat the same thing in R. What's going to happen? Okay. So let us open our R first. This is actually a pretty tough topic. Okay, so you go to your working directory, wherever you find the data in. Where am I? Hey, where am I? Menus. Okay, so I have my algae data set. I import my algae data set. Okay. So this is my algae data set. Actually, I should not import this algae data set. It's like that. Okay, let me mess it up. I'll close the whole thing first. Because remember, just now we have cleaned the data already. So let us just copy the clean data set, excluding the column 1, column A. So I copy from column season to algae and put it in and I save it in just now my folder, and I save it as algae hyphen capital R. Okay. So because just now we remove all the NA already, we want to use it. Just now we remove all the NA columns, right? All the column rows that we cannot use. Okay. Make sure you check your data set is correct or not. Then you close this and import in R. So you go to R. Okay. Okay. So you're supposed to have this regression algae -r, the one that we saved just now. Okay. So you try to import the data set. Import it. Okay. Look carefully. The name here, instead of hyphen, become underscore. So later we have to use underscore now. Okay. Or if you do not want, you can just have algae and capital R. Just delete the underscore. So you save your typing problem. Then you click OK. So this is what you have. 184 observations, 12 variables, which is what we expect us out. Anyone struggling? Yes, it is. Are you okay now? Yes, no problem. So, because remember, it's all over the place now. So this is a human, right? Then you cannot. You have to clean up all the space. These are all the spaces. All right. So far, all here. Any problem? Go to session 17. Find where all is. Okay, you cannot don't know where you are. You are opening the wrong file. You're opening the wrong file because there's a lot of all those NA. It's 200. So 184 only. Okay, so how do you do your linear regression in R? Let's say, so we have type what I type. So I have a model or just M. M equals to, just clean it out for you. So this is easier for you to see. So my model, I want to use linear regression, so the command is LM. Using linear regression, I type in the regression model. So it's algae, theta, let's say phosphate, PO4. I want to find, is it correlated with PO4? No. Use the column name, the capital Algae. Theta. You did that for Anova last week or 2 weeks ago. Okay. Then data equals to the Algae. Yes, it's case sensitive. So in this case, I'm trying to find is Algae PO4, the O, make sure it's case sensitive as well. Just now I forgot. Okay, so this case, I'm trying to fit in the equation of Algae equals to beta 1 of phosphate plus beta 0. Then I press enter, nothing will come out. That's correct, hopefully. To get the table, the regression table, I do a summary of the M, the model. And that gives me the same table that I expect. Huh? What? Then the coefficients actually gives me the estimate, the coefficients as well. It gives me the multiple, the R square and the adjusted R square, as well as the p-value for the R square. The same thing in your Excel. The calculation is slightly different, it will give you slightly different numbers. That's fine. Right? Yeah. So if you want to add more variables, just keep adding here. Just keep adding here. Add more variables yourself. So you want to use phosphate and let's say your nitrate. Test. Can you predict algae growth by phosphate and nitrate concentration? That's what I'm trying to say. Do the same thing. And does it predict bacteria and so on? Okay, so if I predict by just phosphate, my R square value is 0.2099. But if I predict by phosphate and nitrate, my R square increases to 0.2414. So it's a bit better. Yes. I put in the phosphate and nitrate. Yeah, so you can pick and choose. Okay. All right, so that is actually how you do your regression in Anova. Any problem? Surviving, huh? Okay. Now, let's look at this by itself. Let's go back to our Excel. How many of you are still puzzled why on earth it gives you a Anova table? If you look at it carefully, why is R giving you a regression, giving you a Anova table, but the coefficient is actually giving you a t-test result? Okay, let me expand this. You see, the coefficients is actually giving you a t-test result, but regression is giving you a Anova result. Do you find it kind of strange? Why is it not standardized that way? Of course, you know, I already mentioned a few times that there's a relationship between one-way Anova and regression, one-way Anova and t-test. But why does it give you two different things in the same place? And at the same time, do you also realize that the way I do regression in R is very similar to how I will do Anova in R as well? Makes sense, right? Confusing? Okay. So let's just repeat the first part again. Okay, see, yeah? Let's go back to here. If I do, you don't have to do it. Let me do it here. I do the linear regression for algae and phosphate. Okay, and I do a summary for it. That's one. If I were to do the regression, if I do Anova, basically all I need to do is change the function to Anova, and it will give me almost a very similar table. You look at here, the p-value is actually almost identical. In fact, p-value to third decimal place is the same. What do you think is happening? Now, if you look at this table, right? Okay. PO4, sum of square, or rather just look at the F value. And you go to Excel, the F value is the same. Correct? The regression degrees of freedom is 1. The sum of square is 15,856. But if I go to Anova, it is also the same number. So what is then the problem with Anova and regression? Actually, Anova is regression. It is not similar, it is identical. Anova is regression. Okay. Anybody want to see how does it work? Or you're half dead already? If you want, you can go and watch my video. Why Anova is regression? I explained that. My YouTube video. Okay, but Anova is regression is the same thing, which is why it is pretty confusing yet not so confusing. Now it's very confusing for you because it's the first time you encounter it. Okay. To get to this point that Anova is regression, and if you do it in university, it's one whole semester of work already. Yeah, linear regression is 2 semesters of work. There's linear regression 1 and linear regression 2. If you are doing a stats major, that's it. If you're not doing a stats major, then forget it. Yeah. But at this point, to get to Anova is regression, this one whole semesters of work. Okay. I'm just going to tell you all this. Okay, next one is something that did not cover last week, but we'll do a little bit. How do you do two-way Anova in Excel? You know how to do two-way Anova in R, right? Correct? How do you do two-way Anova in Excel? No idea? Okay. Now, okay, let's look at this weird and stupid data set once again. What do you think will happen if I try to use these columns? They are categorical variables, and I use them in regression. What do you think will happen? Do you think it will fail or it will work? Do you think it will fail or it will work? Make a guess. There's only yes and no. You can take a few coins and throw and see what happens. It will fail or work? Yes, this means what? It will work, right? It will work. It will work. Seriously, it will work. So let's try. If I were to do a linear regression, let's say phosphate plus season, which is a bit strange. Your season is categorical, right? But assuming there are 4 seasons, it will still work. It will just break up the seasons up. It will break up the seasons. And because the way it breaks up the seasons, this is why Anova is regression. Okay. And in the last handout for Anova, you heard of this phrase called Anova, right? This is exactly Anova, nothing more than that. But that's really out of the syllabus. Okay. Now let's open a new data sheet. How do you do your two-way Anova in Excel? Okay. So two-way Anova, if you go to your data analysis tab, two-way Anova that's with and without replication. Let's look at without replication in itself. Without replication, that means every combination has only one data point. Okay. So for example, you can say, let's say we do a low salt, medium salt, and high salt. Okay, low salt, medium salt, high salt. Okay, what am I doing? Okay, I'm taking the other way, which is temperature. Maybe I say low temperature, medium temperature, high temperature. Okay, let's say I'm measuring, for example, my cell density. Okay, so low salt, low temperature, after 24 hours, what's the cell density, and so on. So I'm just going to give you some random numbers. Maybe here you have 75, 77, 78, 74, 75, 77. So you have type according to the same numbers. Okay. So 76, 77, and 78 or 79. Okay. So assuming that the numbers here are the cell density, the cell confluence, or whatever thing, up to you. Okay. So how do you do a one-way ANOVA? This is without replication. So you go to without replication. You select the whole data set. And you look at the number of rows per sample. So it's 1. Okay. So it will give you an error. It's actually not easy. It will give you an error. You give it F statistic and give you an error. Okay, let's see. With replication. Oh no, I will select without replication. Oops. Select without replication. Hold on, let me just dump this away first. Okay. So with replication is the let me just delete this. This is without replication. That means everyone is just one data point. So I will select the column and highlight the labels. Okay. Then it will generate the two-way ANOVA table for me. So based on rows and columns. So the rows, this is actually the salt treatment. The column is the temperature treatment. Right. So that is without replication. With replication means that if you take this and for every data point, for every treatment that you do a replicate. So if you do a replicate, all you have to do is to insert the cells and you put another number here, the replicate number, replicate result. So maybe this is 74, this is 76, this is 77. Here you have 77 and 78, 78, 78. So basically what I'm trying to say is for low salt and low temperature, you have two replicates. The replicated result is 75 and 74. Now for two-way ANOVA with replicate, the sample size in Excel must be the same. You cannot have unequal sample size. So with that, let's go to with replication. Select the whole thing. Oops. Select the whole thing. And here it asks me the rows per sample. So every sample I got 2 rows, 2 data points. Okay, then you click OK. So it calculates for in low salt, in medium salt, in high salt, and it calculates the two-way ANOVA for you. So there's actually this interaction. This interaction is multiplied. Salt multiplied with temperature. So that's how. But huh? What? Okay. So this is how you do a two-way ANOVA, and fundamentally that is the end of what we need to cover today. And wait for your friend to come back, then we do a test. What? Test. Let's test today, don't you? Okay, so you can close up all this. Don't save. Okay, so I'm going to stop the recording for here. I'm not going to record the test, but